Hubble. The iconic telescope that's opened our eyes to the secrets of the universe. Expanding our understanding about the fate of galaxies. And introducing us to massive forces we never even knew existed. This is Hubble's amazing universe. The most celebrated telescope on Earth never touches the planet. Hubble Space Telescope orbits nearly 650 kilometers above the Earth, racing around the globe every 97 minutes. Its powerful mirror sees it all. Soaring star factories where new worlds are made. The violence of exploding stars. And a new light on black holes. Hubble is the key that has unlocked some of the greatest mysteries of the universe. But now, the telescope is in danger of being lost forever. Crucial instruments have broken down. A main camera and light-splitting device called a spectrograph no longer function. Gyroscopes that keep Hubble properly oriented in space are failing. Worst of all, Hubble is falling. The 12-ton telescope, as big as a school bus, is slowly spiraling toward the Earth. We are Hubble's only chance for survival, but a mission to save the telescope can be perilous.
I don't know if I could ask an astronaut to risk his or her life to go up to fix Hubble. It's a tough personal choice. But if you ask the astronauts, they do not even hesitate.
Astronaut John Grunsfeld was assigned to the Space Shuttle's final servicing mission to Hubble that launched in October 2008.
Up and burning. 2, 1, and liftoff.
Going to Hubble is a calculated risk. Spaceflight is risky by any means. So in the scheme of things, this is something that I've determined, and on behalf of my family, that it's worth risking my life for.
Why is an aging telescope that's nearly reached its 20-year life expectancy worth the risk? Because Hubble continues to astound us with surprising details about our universe, as it has since its 1990 launch. Astronomers have long wondered where stars like our Sun come from. Jeff Hester of Arizona State University knows that stars evolve from clouds of gas and dust. What he hopes to discover is how these clouds give life to stars. Astronomers suspected that the Eagle Nebula might provide clues, but even the most powerful Earth-bound telescopes couldn't get a clear view. Spring 1995, Hester aims Hubble Space Telescope toward the Eagle Nebula. As he downloads his images from Hubble, Hester can hardly believe his eyes. This is Hubble's first picture of the Eagle Nebula, some 6,500 light-years away. It shows 3 gigantic pillars made of gas and dust. The tower on the left is about 4 light-years tall.
What gives them their shape is the fact that fairly nearby there are some very, very massive, very luminous, very hot stars that are dumping out huge amounts of ultraviolet radiation. And it's sculpting the surroundings.
These celestial pillars have never been revealed in such stunning detail. For the first time, scientists see that each pillar is dotted with small clumps of gas. Could such clumps be a missing link in the birth of stars? Hester calls the clumps evaporating gaseous globules, eggs for short. The image reveals that forming inside some of the eggs are embryonic stars.
What we're looking at is a snapshot of a very dynamic process, a snapshot of something that's changing. As part of that change, next generation of stars is emerging. This one, for example, you can see the little red dot in there, which actually is the star. And that one is an especially nice one. The star at the tip of the egg is actually pronounced.
In the photograph, the eggs appear small, but our entire solar system could fit comfortably inside each one. These hot clumps of gas are the first stage of the formation of a star, and the towers where they hang are rightfully called the Pillars of Creation. Hubble's image of the Eagle Nebula shows us an early stage in the creation of stars. What it doesn't show is the next stage, how stars hatch from eggs. That answer came from images Hubble captured in 1994. Some 1,500 light-years away from Earth lies the Orion Nebula. Like the Eagle Nebula, Orion is a birthplace of stars. When scientists closely examined this image, they discovered tiny dark spots. Flattened disks of gas and dust spots created by recently hatched eggs. The spots are called protoplanetary disks, proplyds for short. The warm orange clump in the center pours in loose material from the surrounding disk. This squeezes the matter in the center of the clump. The pressure grows. The clump heats up. Eventually, it will become so hot that it triggers nuclear fusion, and a star is born. Heat and radiation from the nuclear fusion generates a stellar wind, sweeping away most of the loose matter in the disk. But some of this loose matter remains in orbit around the newborn star. Over time, the debris gathers into more knots and clumps, growing and evolving into a planet.
It really is the case that if you could go back 4.5 billion years ago and look at the formation of the sun and the solar system, that it would be that kind of an environment that you would find us in.
Hubble has shown us the genesis of a new solar system and answered an age-old question of how our own star, the Sun, and our Earth came into existence. Beyond the Eagle and Orion nebulae, even larger star-forming regions lie within the plane of the Milky Way. Scientists wonder if the life cycle of stars is the same in these distant regions. In March 2005, Hubble began relaying images of a new target. The Carina Nebula, one of the largest star-forming regions in the sky. But the raw data sent by Hubble looks nothing like this. Creating images that help scientists unlock the mysteries with this data falls to imaging expert Zsolt Lévay.
I have an emotional attachment to that image, not only because of its aesthetic value, but because of the amount of time I spent on it.
Picture data comes in from Hubble in black and white. Levi assigns colors to these images according to the chemical elements detected by Hubble's instruments. Blue shows oxygen. Red shows sulfur. And green is hydrogen. Levi works for about a year to produce the full mosaic out of 48 separate pictures. Hubble's image of Carina shows a region over 50 light-years across. Here too are the eggs that will one day become stars, encircled by planets. Among the thousands of newborn stars lurks a surprise. Within the cloudy halls of Carina, Hubble detects the death throes of a massive star. For scientists, a dying star is an opportunity to see the future of our own solar system. What these Hubble images show are shells of gas that serve as tombstones. Their quiet beauty is deceptive. These walls of color are the outer layers of a star much like our Sun. As a star runs out of fuel, these layers expand until the gravity of the star can no longer hold them. Eventually, they are released into space. In 2004, Hubble captures an image that gives us a glimpse of our eventual demise. The Helix Nebula. As these outer layers of star expand, they leave behind a searing hot ball of solidified oxygen and carbon astronomers call a white dwarf. Someday, the same thing will happen to our own Sun. The Sun will run out of fuel, and that will cause it to expand into a giant red star. That's bad news for our world. The temperature on the surface of our planet will rise over 1,000 degrees. All life on Earth will perish. A wall of hot gas will sweep over the Earth, through our solar system, and into space. Every planet and moon in its path will be incinerated. The only thing left of our Sun will be a splash of color visible from thousands of light-years away. Like this.
So the human race has its warning. We have 5 billion years to clear out of town.
But even the death of our own Sun hardly compares to a more powerful downfall. Some stars are over 100 times more massive than our Sun. The bigger the star, the shorter its life, and the more violent its death. These stars explode in a massive fireball, called a supernova.
Not every kind of star can explode as a supernova. The sun can't, for example. It just lacks the oomph. It doesn't have the mass that you need to be able to get what happens in the core to make a star blow up. There are a handful of stars in the galaxy that are definitely capable of doing this.
Every star is carefully balanced between the inward pull of its gravity and the outward pressure of the heat it generates from nuclear fusion. When it runs out of fuel, the pressure needed for balance is gone. Gravity now reigns supreme. The star caves in and explodes. The full fury of a supernova destroys the star and everything around it. If the star was near enough to Earth, a wave of deadly gamma and X-rays would flood towards us. It could knock out satellite communications and cause global power outages. In fact, one such giant star has already exploded in our own galaxy. Hubble Space Telescope recorded an image of the aftermath.
The Crab Nebula is the expanding wreckage from a supernova that occurred in the year 1054. The explosion of the supernova was recorded by Chinese astronomers, so we know exactly when the explosion was.
The expanding debris from this 1,000-year-old supernova is still moving into space at about 5 million kilometers per hour. But the image is more than just a snapshot of ancient history. For scientists, the interconnected web-like filaments offer a clue as to the nature of life itself. The basic elements needed to create life are formed in the heart of stars. When the stars explode, these fundamental elements are scattered throughout the universe, seeding distant nebula clouds which give birth to new planets and new life.
The hemoglobin in your blood, when you bleed and it's red, that red color is due to oxygen, and it's due to iron that is in your blood that was created in a supernova. The gold on your wedding ring is created in a supernova. Calcium in your bones was created in a supernova. And so we learn so much about the universe itself when these stars die.
Hubble is giving scientists the ultimate learning experience by monitoring one particular star, Eta Carina, back in the Carina Nebula.
This is a star that is a bit of a mystery. It appears to have about 100 times the mass of the Sun, and that is the upper limit. The more massive a star is, the hotter it is, and the surface of the star is so hot that it can't even hold on to its own gas. It's constantly blowing off a stream of gas.
For over a decade, Hubble creates a series of photos of Eta Carina. The photos showed two enormous lobes of superheated gas erupting from the surface. Although Eta Carina is a young star, its huge mass makes it unstable. This star will not survive for long.
Eta Carinae is one of the very few stars that we can point at and say, yeah, that one's gonna go.
When Eta Carina goes, it will become one of the most devastating supernovae ever recorded.
When the light from the explosion reaches us, it will be an extraordinary sight. It will be almost as bright as the full moon. All that light concentrated into a point of light in our sky. It will cast shadows at night.
The fireworks will begin when the star runs out of fuel. The gigantic star will destroy itself in just a few seconds. The core of the exploding star will bear the full brunt of the catastrophe. When that happens, it will leave behind one outer space phenomenon that has long captured the imagination of stargazers. A black hole. The mysterious black hole phenomenon is the product of the violent and powerful explosion of a supernova, at least in theory. Before Hubble, there was no conclusive proof that black holes existed at all. The modern concept of a black hole comes from Einstein's theory of general relativity.
If you take matter and you make it massive enough, dense enough, the gravity will be so strong that you'll create a region of space that light can't get out of. It truly does make a hole in space. You can get into it, you can't get out of it. It's sort of like a cosmic lobster trap.
According to Einstein, a black hole begins with a very large star. it must be at least 4 times bigger than our sun.
A black hole is a simple thing. It is a hunk of matter which somehow has gotten so small that the gravitational field right around it is so strong that light cannot escape from it. So even if it tried to emit radiation, the photons would fall back. They would be sucked back by the gravity of the black hole, and it would look invisible.
During the blast of a supernova, the inner core of a star collapses into a single point, smaller than a pinhead. Astronomers call this single point a singularity. A singularity is an object with no length, width, or height, yet it retains most of the gravity of the original star. One of the primary goals for Hubble was to prove once and for all whether or not black holes exist. But how does one search for an invisible point? Astronomers decide to direct Hubble to examine the exact centers of galaxies. It is a wise decision. What they discover is that the stars close to the center of galaxies zoom around at very high speeds. This is not how stars normally behave. Most stars move along at relatively slow speeds. But down in the central hub of galaxies, stars are being thrown around by the gravity of something that is massive yet ultra-compact. There can only be one cause for this effect: the fabled black hole. Further evidence of black holes comes from Hubble's images of a mysterious jet some 5,000 light-years long. The jet is piercing the heart of a giant elliptical galaxy called M87. The jet in the galaxy M87 is caused by enormous amounts of gas and dust piling onto the black hole. There's so much material that a traffic jam occurs. The gas and dust back up, forming a disk. Some of this material escapes and creates the jet. The black hole is showing itself with a parade of light. The connection between a galaxy and the black hole in its heart is not yet well understood. But astronomers believe that black holes play a part in the formation of galaxies.
As far as we know, every big galaxy has a black hole at its very center. We don't know exactly how this happens. It must have something to do with gas falling in as the galaxy evolves.
And this has been one of the revelations come through a space telescope, is the real deep and fundamental connection between black holes and galaxies done by looking at M87, but also, dozens of other galaxies.
Before Hubble, black holes were merely a concept, an unproven part of astronomical lore. Hubble Space Telescope has changed that forever. The violent forces that create stars far off in space also shape our own solar system. In the summer of 1992, comet Shoemaker-Levy 9, or SL9, passes too close to Jupiter. The 1.8-kilometer comet is trapped by the giant planet's gravity. Then, SL9 breaks apart. The fragments spread into a long single line which Hubble showed in an image called the String of Pearls. Data suggests that these pearls would soon collide with Jupiter. So planetary astronomer Heidi Hammel submits a proposal to NASA.
We had known for many, many decades that collisions are an incredibly important part of solar system evolution. You look at the moon and you see craters. So you know that collisions are important. Even on the Earth, we've known for decades that collisions have played a big role. But we never have had an opportunity to see a collision.
Shoemaker-Levy 9 would show that such collisions are not just part of the past, but the present and maybe the future. Part of the challenge of Shoemaker-Levy 9 is getting Hubble to follow an event in real time. The telescope usually looks at processes that unfold over millions of years, but the comet's death would happen rapidly. In July 1994, the team gathers at the Space Telescope Science Institute in Baltimore to watch the comet make contact with the planet.
We didn't know what was going to happen when Shoemaker-Levy 9 hit Jupiter. And it was really possible that nothing would happen at all.
The first image of Shoemaker-Levy 9 came in. It seemed to show no signs of impact. But then, new images came in.
So there's a red spot, so you know. Atlas is
Oh, wow.
Yeah, that's it.
Oh, my God.
That's it.
Look at that. The planet had rotated enough that the impact site was visible on the disk, and it was huge.
The team was watching the comet hit the planet in real time. This was cosmic history in action. Reporters and cameras were standing by in an auditorium above.
And at the same time, on the screen of the press conference, Gene Shoemaker was saying,
If we should see these things at all,
and we were downstairs going, woo, look at this, amazing. And we go, oh, we have to show this. You can't let him sit up there saying we don't know. We know.
Pepper shot, she's going in. She's going in. Hammer 3. Come on, she's bursting in. She's bursting in. Go.
And I stood on the side, and they were all on a little table, and
and I think we may have some up-to-date information from Heidi Hammel.
I have a raw laser printer output. This is as raw as it gets. We can actually see the impact site itself.
For an entire week, Hubble captures images of Shoemaker-Levy 9 as it mercilessly hammers Jupiter.
We calculated the heights of these explosive plumes out of Jupiter to rising something like 3,000 kilometers out of Jupiter's atmosphere. It's huge. It's planetary-wide scale. What there was left was clouds that had been seriously disturbed over thousands and thousands of miles, seriously disturbed up to temperatures of tens of thousands of degrees. So if an object like SL9 had hit the Earth, it would have been a bad day.
Hubble's pictures of the comet impact prove that the kind of violence that formed our planet billions of years ago continues through this day. Shoemaker-Levy 9 shows a devastating day on nearby Jupiter. But when Hubble turns toward an empty patch of distant sky, What it finds will rock the scientific community. In the winter of 1995, a series of commands are sent to Hubble's onboard computer that turn the orbiting telescope toward what is apparently an empty part of the sky. Hubble's powerful gaze locks onto this single region of space for 10 consecutive days, creating a series of exposures that would be known as the Hubble Deep Field.
The Hubble Deep Field was a pretty astonishing idea. Take a telescope out in space and point it at one part of the sky and let it sit. Just take an exposure, and then take another one, and another one, and another one, and then add them all up. And what do you see when you do this? That's what the Hubble Deep Field is. It is deep in that we're seeing very deep into the universe. And you see galaxies. Thousands and thousands of galaxies. A crowded, dense field that looks like you're taking a picture of fireflies out in a field at night. And yet this is an empty patch of sky.
Every smudge of light in this Hubble picture is a galaxy containing billions of stars. These galaxies are captured at various stages of evolution. From a time near the birth of the cosmos to the rise of spiral galaxies like our own Milky Way, scattered here and there, in the Hubble Deep Field are the smash-ups of space. Galaxies crashing into and cannibalizing each other.
We estimate that there are hundreds of billions of galaxies in the universe. But it's only until you see that Hubble Deep Field and you understand that you're seeing a tiny little patch of sky. And yet it is filled to the brim with galaxies. And that's telling you that this universe is an astonishing and crowded and wonderful place.
The entire history of growth and change in galaxies is written in this single image of the Hubble Deep Field. What may be Hubble's most profound discovery cannot be seen at all by any means. Something with so much power, it holds the entire universe together. For a number of years, astronomers like Kim Weaver have been surprised by the way galaxies behave.
Our observations of things we could see, like galaxies, weren't making a lot of sense to us. For example, how a galaxy rotates.
The arms of spiral galaxies seem to move faster than the laws of physics would allow. Astronomers spotted other oddities as well.
You can have clusters of galaxies that have hundreds to 1,000 galaxies in them. These clusters of galaxies are still bound to each other. The galaxies are still orbiting after all this time. Why are they bound to the cluster? There's something there creating gravity, creating the bending of space to hold these galaxies in place and to hold galaxies in their rotation that we're not seeing.
Astronomers hypothesize that galaxies are surrounded by a halo of unknown forms of matter. This matter acts like a glue that holds the universe together. They call it dark matter. Though we can't see dark matter, one astronomer has discovered a way to find it.
We took the Hubble Space Telescope and over 2 years slowly pieced together a mosaic of 600 images, tiled together a large patch of sky. in which we could see about 2 million faint galaxies. And this was the Hubble Space Telescope Cosmos survey. It's the largest ever survey taken from space.
The survey revealed that stars and galaxies are born from ordinary matter, trapped by gravity inside clouds of dark matter. This 3D plot of dark matter clouds, charted by Hubble for the first time in history, shows how dark matter forms the very structure of our universe. Soon after the Big Bang, the gravitational scaffolding of dark matter formed the basis for evolutionary change throughout the cosmos.
And we in fact owe our entire existence to this scaffolding that's set up of dark matter in the early universe.
As important as it is to our very existence, astronomers so far have no idea what dark matter is. This table shows us every element in the universe that we commonly experience on a daily basis. All of the physical matter that we can see, touch, taste, or feel is on this table. But not dark matter. Thanks to Hubble, astronomers found a way to locate and measure it. What they found is that there is 5 times more dark matter in the universe than physical matter. But even if we add all the dark matter to all the physical matter that forms stars and planets and people, it turns out that we are still missing about 2/3 of the universe. So, what is the rest of the universe made of? Once again, scientists turn to Hubble for answers. The Hubble telescope is changing our understanding of reality. Since the 1920s, astronomers have known that the universe is expanding. They assumed that gravity would one day slow the expansion down and perhaps even cause the universe to halt.
I know the universe is slowing down. The question just is how much.
The answer to this question would settle the debate about the age and fate of the universe. And it became a race.
There were 2 teams that didn't much like each other. They were trying to measure the rate at which the universe has been expanding at different times in the past and compare it with the rate at which it's expanding now.
The way to check comes from Hubble. It finds supernova explosions in remote galaxies and uses the light from the explosion as a yardstick to measure the distance from Earth to the galaxy. But Hubble's findings do not fit the accepted model for the expansion of the universe. The galaxies with supernovae are not just moving away, they're moving at an accelerated rate. Hubble's results convinces astronomers that they must think of the universe in an entirely new way.
You toss a ball up, it comes back down or it slows down. What you don't expect is the ball to speed up and speed up and speed up more and more and more. That doesn't happen.
But it does happen. According to Hubble's evidence, the universe is expanding more and more quickly. The only explanation is as simple as it is unlikely. Something is causing the expansion of the universe to accelerate. An unseen force called dark energy.
Dark energy is another manifestation of a familiar force. So gravity is a familiar force, but we've never seen it act this way before.
But the darkest part of this mysterious force is its future. Over time, it will grow in strength. This means that one day, dark energy will become stronger than gravity. Stronger than even the forces which bind atoms together.
Every bound thing becomes unbound, including eventually at the most subatomic level.
Our universe, it seems, is living on borrowed time. The universe will one day end in a cosmic apocalypse that scientists call the Big Rip.
It's what we get for daring to look at something. We're outside the envelope. We didn't expect this at all. It is a tremendous change in how we think about the universe.
Imagine we know nothing of the sea, and one day we discover the ocean. We find to our surprise that 3/4 of the world is covered by the ocean. But we have no clue what is in the ocean or what the ocean does. This is where we are today with dark energy.
The continued study of dark energy may be the single most important reason for keeping Hubble on orbit.
But how much longer can we keep Hubble flying? Nearly 20 years after its launch, the Hubble Space Telescope is still learning new tricks. When the shuttle Atlantis undocks at the end of the servicing mission, a new wide-field planetary camera 3 will become functional, widening Hubble's range. Another new tool, the Cosmic Origin Spectrograph, will tell us more about the way dark matter affects distant galaxies. But even with new hardware, Hubble's days are numbered, for the shuttle will also be installing a device that will end Hubble's long journeys into space.
At the end of the mission, when all the work is done, before the final moment that we go back in the airlock, and I'm absolutely sure I'm going to take either one last grab on the Hubble or one last look. I do believe this is the last time people will visit the Hubble Space Telescope. And after all that so many people have invested, I think I will vicariously for them and for real for me, I'll be kind of giving Hubble that last hug before we send it on its way to what really will be an entire new journey of discovery for Hubble.
It is difficult for me to think of the end of the mission for the Space Telescope because right now it's in prime productivity, or rather will be once we're able to fix it up again. Demand for it is strong. The capabilities are unique and will remain unique. It will be a loss when the Hubble can no longer take observations for us.
On the day that happens, the telescope will receive one last command to shut down and return to Earth. The orbiting telescope will burn up as it re-enters the Earth's atmosphere and pass into history. Controllers want to make sure that the enormous telescope falls into the Pacific.
It'll be a poignant moment for those of us who have used Hubble. It's just been such a fabulous part of our lives and allowed us to do so much wonderful work. But I think at the same time we're looking forward.
The next generation of space telescope is called the James Webb Space Telescope and is scheduled for launch in 2013. The Webb telescope will go beyond Hubble, literally. It will be placed beyond the Moon, poised in delicate balance among the gravitational pulls of the Earth, Moon, and Sun.
James Webb Space Telescope that's coming along after Hubble has some hope of actually directly imaging a planet around another star. Someday we hope to not only find Earth-like planets, but to detect their atmospheres, chemically analyze their atmospheres, and see if there are signatures of life. This is not science fiction. This is not fantasy. We are on a fast track.
The Webb will take science beyond Hubble's range, but the Hubble will always be the first. The first space telescope, and the first telescope for every man.
Scientists use it, but the public have more access to the pictures that were brought down from this telescope than ever before. And so it revolutionized astronomy as far as the public was concerned. If you wake up somebody out of bed, a random citizen in this country, and say, name a telescope, they're going to name Hubble.
Hubble is about the frontier. Hubble is about discovery. Hubble is about what's new. Going into the future, I hope that we find some way to maintain that capability, because the instant it goes away, we're blind.
It has circled the Earth thousands of times, whirling around us again and again. Hubble has been the wide eyes of some very curious beings. It has given us astonishing images, taking the human mind to the beginning and end of time, beyond our own ability to wonder at the world.